Okay, this is the Chapter 9 Part 7 video. In this video, we're just going to go over a couple of examples of elimination reactions. You can see in this first example here, we're going to look at dehydration. So in this case, we're going to start off with an alcohol in the presence of a strong acid like sulfuric acid. You can also use H3PO4. We also need to heat this reaction up. We can cause this reaction to do an elimination. So remember that our alcohols are not good leaving groups. So what's going to have to happen mechanistically is we're going to protonate our alcohol, and then that can be our good leaving group. Depending on the substrate, it can go through potentially an E1 mechanism. So in these examples, we have tertiary substrates, and so you can see that they can go through an E1 mechanism. So let's look at some examples, let's of this. You can see here that we have the more stable alkene being formed. Again here, the more stable alkene is the larger or greater product, and same thing down here. So the next slide shows some possible mechanisms, and you probably want to walk through these examples and make sure that you can do them on your own. As you can see here, our alcohol is protonated by sulfuric acid. Okay, the acid here, this is the hydrogen that shows as the acid source. Our HSO4 minus is going to be the byproduct. Once you've protonated the alcohol, it can now fall off as water. Water is a good leaving group, whereas hydroxide is not. So you have to protonate the OH first, or it cannot fall off. As long as we're going to form a nice stable carbocation, this reaction will work well. And then you can see that the water then can act as our base in this situation, pull off this hydrogen, and the electrons can come down and form our alkene. So, because this goes through a E1 type mechanism, we're going to have an easier time dehydrating our tertiary alcohols and a harder time dehydrating our primary alcohols. They would have to go through an E2 type mechanism, and that's going to be a little bit more difficult in this situation. Because remember, E2 reactions are promoted by strong bases, and we're using water here as a base, so this is not going to work well as an E2 mechanism. You also have to be on the lookout for carbocation rearrangement. Anytime we have formation of a secondary carbocation, you have to look around and check to see if it could potentially form a tertiary carbocation. So in this example here, you have an alcohol that is being dehydrated by H3PO4. It's not drawn out, but the H3PO4 would protonate the alcohol. The alcohol would then fall off and form the secondary carbocation shown here. So once you form the secondary carbocation, you can either have the elimination occur directly. So you can see that the water over here can pull off the beta hydrogen. There's really only one possible beta hydrogen in this case on the CH3, but this product is very minor, only 3%. The major product is going to come from a methyl shift. So this CH3 group and its electrons are going to jump over here. That gives us a more stable tertiary carbocation. And this tertiary carbocation can then do an elimination reaction. Now, it has lots of beta hydrogens. You can see that this CH3 over here, which is equivalent to the CH3 on top, if either of those are pulled off, if either of those beta hydrogens are pulled off, it's going to lead to this product on the right. But this alkene is less substituted than this product on the left over here. If you pull off a hydrogen from the CH, you're going to end up with a more substituted alkene, and this is going to be your major product. Okay, so this is a good example of a dehydration with a carbocation rearrangement. Here's one more example. You can see that in this case, we also have a methyl shift, but it actually involves a ring expansion. So if you're looking at this alcohol here, we're going to get protonated by sulfuric acid. Water is going to fall off, which gives us a secondary carbocation. And then what you see here is a ring expansion happening. So usually what I do to kind of understand what's going on here is I'm going to label all of the carbons here. Okay, so now you can see, hopefully you can get a better idea here what's happening. So the electrons between 3 and 4 are going to move, and 4 is going to become bonded to what they have labeled as carbon 2. So if we draw this out, okay, so here's 5, 6, here's 4, and here's 3. So now the bond between 4 and 3 broke, right? 3 is bonded to carbon 2 over here. 2 is also bonded to 1. And so now 4 is going to move its electrons over to 2 here. So when that happens, 3 lost some electrons, and 3 is going to have that positive charge. So that's essentially what's happening here. If you look at this diagram, this one here is positive charge. This is carbon 3. Okay, over here is 6, 5, 4, and this is 1, and then 2 is right there in the middle. Okay, so that is showing you the ring expansion. And then you'll notice that we still have a secondary carbocation. So there's yet again another hydride shift. So now we're doing we did a methyl shift or a ring expansion, followed by a 1,2 hydride shift. And that ends up with a positive charge on carbon 2. And finally, we've gotten to our tertiary carbocation. This is the one that can then react with the base, do an elimination reaction to form an alkene. So this is our product that we're getting over here. So once we've gotten to the product, you'll notice that it is the most stable alkene. We're pulling off the hydrogen over the beta hydrogen over here that gives the most stable alkene. The other option would be to pull a beta hydrogen off of the CH3, but that would give you a less stable alkene product. So of course, we're going to try to form the more stable alkene.